Yes. So let's continue with transformer architecture. My name is Rajathan Gulab More, and now I would like to explain what is transformer architecture. But before going into transformer, we need to understand how we end up with transformer, how what is its architecture, how it works, why we need to use transformer, what we were using before that, what is RNN, what is LSTM, what is attention, what is embedding, what is encoding, what is multi-headed attention, and all that things. What is sequential, what is parallelism, and that kind of things. We need to have some brief ideas before going into transformer architecture. So what we were using before transformer, we were using RNN architecture. I think everyone is aware of RNN, but for those who don't know, if you ever have used Google in olden days, uh, even today only, if you type something, next word will be predicted and next sentence can also be predicted. That kind of next word prediction based on single output is sentence, basically sentence prediction, or basically next word prediction, or sentiment analysis type of things. That kind of be done with the RNN architecture. So RNN is basically used for predicting the next word. It is sequential in nature. After I think everyone is aware of bag of word, TF-IDF, that kind of embedding techniques, right? I will give just brief overview over that. So let's consider we have a sentence of any sentence. I'm going to the market, that kind of sentence. So first of all, it is complete sentence. It is in the word format, but machine cannot understand word format. Is usually converted to numerical format. So how do we do that? First of all, we will change this sentence into word vector, like I, comma, we, am, comma, going to, and comma, market. And each word will be then converted into a numerical format. Like corpus will in this example will be of 5 words. I, comma, I am going and market. This 4 5 words. So and based on suppose we are using bag of words. Then in bag of words, the column list will be I am going to the market, and then target columns means uh, in the bottom we can check it corresponding to those already present words in the corpus. Like if I am entering I, then is I present? I is present at the first location, then it will be one, and this is am I not. So it will be zero. Then going compared to I is not I, so zero and zero zero zero. As similar to M, M with compared with the I, M is not I, so it will be zero, and then M is M, then it will be one, and then going and M, so it will be zero and zero zero. That kind of simple representation we can consider in case of bag of word kind of thing. TFI or DF will be a little bit tricky, and I am not covering that in this video. So one minute. Uh, so that kind of numerically represented vectors can be used for prediction. I think everyone is aware of deep neural networks and how its architecture is. It will have uh, multiple hidden layers and then output layer, input layer, right? So this 1000, this is the input layer, and all these dots can be this dot and circle. This arrow is pointing towards it. First one, this will be the hidden layer, and it can have multiple hidden layers, and based on the much output and how we are training it, which kind of model we are using, and then based on that hidden layers, some output will be generated. Like in basic neural net, deep learning also, we can guess basic neural network also. We can guess that it will generate some output. It either can be a singular word or a vector, right? Usually it is a vector, based on prediction, and then we use softmax layer to get the either a singular output or that kind of things, right? If it is classification or prediction type of model. Here also, we are sending 100 as a input layer into a hidden layer, and some output vector will be generated, right? That kind of output vector, instead of going to softmax layer, we are sending into other words inputs, like 0 1 0 0 0 will be a second word, like M. It will be also input layer, and then its input will go into the neural network layer, hidden layer. Along with this input, previous like previous words output will also be integrated into this and will be gone into the neural network. And then will similar things will be the going and then to the market, that kind of thing. And then based on all this, at the end, one output will be generated. Right. So even after knowing this, I think many will understand that it has some problems. Like, first of all, it is heavily dependent on the previous words and how it is knowing which was the first word. Like, am I going to the market? I'm very happy and it is raining, right? So, how raining is, it means if the sentence is wrong, how till the we get to the raining, how it is still attached to I am going to the market, right? If the sentence is too long or if it is complex, how and it is sequential, is it slow? And if it has only certain number of hidden layers, then how it is tracking all these parameter, if those parameters are even good, and if basically all these neural networks, hidden layers, number of hidden layers are similar for all these words. Same hidden layers are used for each word. So if the sentence is huge, obviously the parameters will be not trained on particular words. It will just be uh, mostly heavily dependent on the current word, not the words we started with, or even the key information giving words will be forgotten and the recent word will be given most priority, right? So that is the one many drawbacks of RNN. So that's why we went with LSTM. There are some of the problems with RNN is mentioned here. It is sequential, like I mentioned. It does not understand proper context. It also don't have any state mechanism. Like if even if you ask something, let's not get into it. But it does not understand the context because it is only depending on the previous word, not all the sentence. It is not grammatically rich because how it will just it can predict the words properly, but it is not guaranteed that it will be making too much sense or will be properly uh, generated. It is sequential, so it is not utilizing GPUs properly. And vanishing and exploding gradient problem. Like if you know deep learning, you know that if there are multiple layers, as we keep on adding layers or as we go forward, vanishing and exploding gradient problem is very common in deep learning, right? To solve some of this problem, we went from RNN to LSTM. But LSTM is a long short-term memory. It is made with multiple gates like input gate, output gate, forget gate. It is built in such a way that it will remember keywords for longer time, but still it is sequential, still it will be slow, and still it will not be grammar-rich. It will be more, means it will be better than LSTM, but it won't be that much good, right? Some of these drawbacks, which are similar to RNN, is mentioned here, like it is sequential, it cannot understand context, not grammar-rich, not GPU friendly, and it is improved version of RNN, but not that good. It still faces vanishing and exploding gradient problem, which because we just have introduced gates here so that it can understand, it can retain important words for longer period, but still it it cannot uh, m- avoid this vanishing exploding gradient problem because we have not done anything to solve it, right? This is the basic. In the bottom we have basic RNN structure, and that is the basic RNN structure, that it is recursive, like the name says. So yeah, so that's why we went with from LSTM to transformer. But what is transformer and why we need it? Why we need it is clear that to overcome some of the shortcomings of LSTM, RN, and all other models, we came to transformer. On the left hand side, you can see the basic RNN, transformer architecture, and it is not the standard, means it is not that hardcore that you have to use this structure only. Like in ChatGPT, we use it is decoder based model. Like it is based on decoder part, means in the image you can see on the right hand side it is decoder, and on the left hand side it is encoder. And BERT kind of model is heavily made with encoder part, right? So structure can be little changing, and it all depends on case to case basis, so people can change it. Basic structure is input word. Suppose I will be uh, a word. It already tokenized. It is a word. It it goes into embedding layer. Embedding means it is converted into a numerical format. So let's suppose we are using linear regression. So do we know which line is perfect at the get-go? We don't. We don't have any idea also. So we just draw a line randomly, right? And then we get some parameters, and then as we train it, the parameters get adjusted and with the to have the least loss, and based on that line shifts and get into most appropriate position, right? Here also, at the time of embedding of word I, it will have some numerical represented vector, right? It will be a big, suppose, PyTorch. mm, uh, Suppose a vector is there, a big vector, and with numerical means it will have multiple values, not correctly representing the word. It is just representing the word as of now. Okay, and before, as you know, unlike RNN and LSTM, it won't have I then am then going to the market. It won't have sequential pattern. It will have parallelism. So I will go as am as going as market. Okay. So but how this architecture will know which word comes first, right? Because while training it is very important that parameters learn correctly. Without knowing which word comes first, the parameter will not understand the context and it will be trained on wrong kind of information, and hence the model will be unusable, right? So its prediction will be actually far worse than even in LSTM and RNN, because at least in that case we had some sequential understanding. Here, if we are using parallelism and no position understanding, then it will be unusable. To avoid that, we use position encoding layer. So what is position in position encoding layer? In forward slides we have that explanation, but the brief overview is, suppose a current vector of I is 1, 2, 3, 4, that kind of, and we have concatenated one other matrix into it, like 0, 0, 0, 1. Okay, and then AM will have some other matrix. It will be concatenated with 0, 0, 0, 2. It will be very basic to understand. So that kind of concatenation will be done for entire corpus, and then will be fed into the transformer architecture. So that while training, the parameters will be trained such that it can understand, okay, this word has this kind of vector at the end of 00010. Then it can understand, okay, this usually comes after 0.009 and before 0.0011, right? Some kind of understanding it can have. To add that understanding layer, we had position encoding before into the this embedded vector so that while training the parameters can understand, okay, which word come first, which come later. It will be also benefits for the grammatical understanding. So then we go into the transformer architecture. Okay. Okay. So um, you have attention head, multiple. Don't focus on multiple attention head. Just focus on attention head, norm layer, feed forward, and then mask attention, multi attention, feed forward, dense layer, softmax layer. Okay. So they are not okay. These names, some of these names might be right. So, what I was saying. So, okay, there are multiple attention head, feed forward. Feed forward is just deep neural network and add norm layers. We will understand each one by one. Let's get an overview of what is attention head. Okay, so I think everyone is aware of CNN architecture, right? CNN, we also have image in numerically represented form, like if you have seen that famous handwritten image example, right? So based on that input, a model will be able to predict it is 7, 8, 9, or 10, right? So for that, also in CNN we have multiple filter layers. Each filter layer will be, first of all, what is a filter layer? It will be a matrix that can be multiplied with the input vector, and some output vector will be generated that will be heavily can be used for predicting one particular feature. Like in case of CNN, if the filter of edge is multiplied with the incoming vector, then output matrix will be heavily used to predict the edges of the image. And similar can be done with the color, depth, and distances from the object, facial expression. So, right, facial expression and that kind of things, right? And in here also, we at inside head also we are using multiple features, multiple filters. Primarily, we have filter vector of Q, WQ, WK, WV. Okay, so why we need that? Because we don't know. Suppose in a paragraph we have apple mentioned. So how is apple dependent on particular other words present in the paragraph? Like apple can be present on uh, fruit, trees, and other things, and it can also be dependent on electronics, price, and shipment, containers, that kind of things, right? So based on other words present in the paragraph or corpus, we can have understanding of the word if it is apple phone or apple fruit. Okay. So to understand that we use Q attention head. Okay, that is basic functionality of attention head, and to get clear idea, like even in that attention head will be doing that only. Mm, and let's go from the beginning. Input vector will be some embedded vectors. It will be then added with the position encoding. Then it will go into transformer attention head. Attention head will just convert this I vector into a new kind of vector it will be rich in context depending on other words present in the sentence, right? That is the basic word of attention, basically. And this add norm layer is just because in this add norm layer is present everywhere in this transform architecture, which is to avoid this vanishing and exploding gradient problem, like we have seen in RNN and LSTM. Okay, it is done so that even if the sentences are things are too long, it will still have the context of how it started with, like meaning, initial meaning of this word I will still be present even if we are added. It made it context rich with the other, and embedding is changed. Even after feed forward neural network, the outputted vector will be prediction of input matrix will be converted into a different kind of matrix based on the deep neural network of its parameter understanding. It will be again added with the this add and normalization layer. And this all add and norm layers are so that it won't forget the context of how it started with. So that is all this add and norm layer is. Feed forward neural network is just deep neural network. So let's begin, and this dense layer is also this feed forward like feed forward neural network. A softmax layer will be just like mm, basic neural networks prediction. You can also consider logistic regression of how we get a softmax at the end to predict if it was mm, true or false, that kind of prediction, right? So that is the softmax layer. This is the basic understanding of what is the transform architecture. So let's begin. Embedding will be a numerical representation of word. If embedding is done correctly, then one word's numerical representation can be expressed with the form of other words. Like here, we have queen minus is equal to king minus man. So mathematical representation of king means numerical representation of king minus numerical representation of man can result in numerical representation of queen. That kind of matrix multiplication matrix calculation can be done, and to miss can be done if it is done properly. This is done so that if uh, as you can understand, then king and queen will be in somewhat similar zone, and poor man poor woman will be in other zone, or animals will be in other zone, because numerical representation of all these features will have some similarities, and if we plot them correctly, then this kind of groups can be formed. Means it will form automatically if embedding is done correctly. And like I said, if all the words are going together, then how is model means how is the transform architecture able to understand which word is coming first? Here I have given one example: mouse at the cheese and cheese at the mouse. So meaning is completely different, but we have to train the model so that it will understand means proper meaning, which is wrong, which is right, and to training we need to provide proper input at least. If otherwise it will be garbage in garbage out condition. To avoid that, we add positional encoding. Positional encoding is generated with the either sign, cos, or that kind of trigonometric functions, so that it will have some predictability into it. It won't be random, and a pattern will be there with each input, right? So for that we use sinusoidal that kind of input, and it is concatenated with our current input. Like I will be added with this position encoding, like I have explained with previously. Uh, Here I have just explained this CNN filter thing. Suppose don't look too deep into this example, this equation. Suppose consider this. Let's consider Apple only. So Apple This word apple will be our uh, on the right hand side on the top column, the top row. See this. Apple will be our x. Okay. It will be multiplied with some vector. Like in CNN also we multiply with this filters. Here we multiplied with some vector and output will be a matrix. Okay. So let's call it Q matrix. You can keep it aside. Now we also multiplied apple with this W and apple with this V. Okay. But let's so we are basically multiplied all this vector with other vectors. But main thing comes when we are multiplying this, suppose in second row of right hand side image, suppose instead of apple it is phone. Okay, so then phone will be multiplied with this one matrix like in CNN filter. Some output will be generated. It will be our key matrix. Okay, so for now just focus on q matrix and k matrix. So q matrix is of apple, k matrix is of apple also, but let's consider with phone. Okay, so q into k in this left hand side image you can see we are doing matrix multiplication. So in matrix multiplication we are multiplying this two matrices q and k transform. K transform is just so that it can do matrix multiplication. If you know about matrix multiplication, then it will generate some output. Okay, and then that output is as it should not be out means too it should not be too big an output. It should be in certain range. That's why we are dividing it with the dimension of k matrix. Okay, it otherwise there is no need for that. And then we are sending it to the softmax layer to get why we need softmax layer. If you know the basic understanding of softmax layer, if the value is uh, basically we need a probabilistic value to get that we need softmax. It will convert whatever numerical value we get into 0 to 1 format. Okay, so it will convert suppose a big number into 0.98, that kind of thing. Okay, and this v matrix is the value matrix. What is the value matrix? Value matrix is up apple into this filter wv. It will give our one value matrix. Phone into this filter v will give a second value matrix, and this love into this filter will give a third. Means multiple value matrices will be created. Similar with the k and similar with the q. For each word, we will have this kind of things. Okay, and so and this so why we are doing this? We are basically doing this to understand how this love is the Z matrix. Okay, the Z matrix at the end. Focus on this red line. So this new embedding of love will be a result of attention score, that is the softmax output of a previous embedding of love. This E love is value matrix. Value matrix which we got from this love matrix into this filtered of WV plus 0.1 is the softmax output of love into Q love into Q K apple. Okay, and this is the value matrix of apple plus Q love. Q love means query is love into K phones into the value matrix of phones. So basically, we are converting this embedding of each word so that it will have some relevance of all the other words. It will understand how each word is dependent on others. Why we are doing this? Currently, in the at the very first step, we just had embedding, randomly generated embedding. If it was proper, means it was good embedding, but it was very independent of all the other words. So now we are changing this embedding so that it will have some corpus understanding of all the words. Okay. So here apple is and this attention score means how much one word is dependent on other. Love is heavily dependent on itself, but very less on other words. Apple is heavily dependent on itself and very dependent on phones because I think in corpus which it will have multiple words that will correlate Apple with the phone. Phone is very less dependent on it's relevant to love very and heavily relevant on Apple, heavily relevant on itself. That kind of understanding the new embedding will generate from this attention head. So basically here, just have explained what is the mechanism of this. Right, this we are dividing this with dimensionality k because in this example, like you can see 0.7 and 0.3. After this softmax, it will be heavily shifted to 0.9 and 0.10. Mean probability of 0.7 will be very high, 0.3 will be very low. To avoid that, we divide it with this square root of dimensionality k, so that the difference will won't be that high. Means 0.7 and 0.3 will be reduced to a smaller number, and hence after softmax layer, the values won't be that uh, far apart. Means it won't be biased toward one particular word. And if you know the famous example, I saw him with the macroscope, and oh sorry, she saw him with the microscope. She saw him with the macroscope. So based on this highlighted, we can understand that it will have different meaning based on who are we asking it to. To avoid that, we use multiple set of QVK filters of QVK, QVK, QVK. So multiple layers will be multiple attention heads will be there, and based on that, we will get this different kind of QVK matrices. Based on that, we will get different embedded outputs, and based on that, we will get one final concatenated result of all this multi-headed attention so that we will have all the perspective of this single word so that and more the parameters are better because we already have advanced GPUs and all, so parameters sinus is not good for current conditions. So we can add multiple parameters, more the parameters, the better. With the different kind of filters, we can have different perspective and better understanding, deep understanding of each word in the sentence. So that was the multi-head attention layer, self attention. After that, we add and normalization layer. So uh, basically, add and normalization layer is just so that previous outputs won't be forgotten as we go forward. That is the basic idea. So basically, we know uh, add no layer will be just that previous I vector will be added into this newly generated Z vector, right? And so that it will have previous understanding of what the word was, and it won't be forgetting that because we have multiple vectors. So vanishing and exploding gradient problem will be obvious. So to avoid that, we are using this means not multiple parameters and too many layers. So vanishing and exploding gradient will be obvious there. To avoid that, we are adding previous uh, embeddings into the current embedding, and this will go on till the end so that it won't forget what was the initial thing. And normalization is so that after adding this x and z, means z will be the newly embedded same word, and x will be this previous embedding which was the input. To after adding we normalize it so that it won't have miss suppose a matrix have some section of even in machine learning we do normalization so that it won't have bias toward one particular section or column. Here also we don't want certain words to have too much different bigger meaning and certain values to have different meanings and other numerical vector components to have very significant meaning. So we convert it into a smaller range so that it won't have any skewness or any bias factor into it because even after this we are sending it to feed forward neural network, and if we send that kind of data into a feed forward neural network then without normalization then it will have a poor understanding of what the word is saying, what it won't be training properly, it will be garbage in garbage out condition. So this normalization will be our small EDA on this before sending it to feed forward neural network. And feed forward neural network is just bunch of hidden layers only. It will be parameters that will learn as basic forward and backward propagation. So and then train the parameters so that it can then give an output based on this trained parameter. Up till now, we have block is completed, and this was all this as per the attention all we need. And after encoder block, we go into decoder block. Here we have seen suppose it is a suppose translation. So all this word will be going to attention block at once, and the output matrix will be going into decoder block, and then output will be generated. So uh, encoder and decoder transformer, just like this, we also had encoder and decoder blocks in LSTM and RNN also, but they were sequential, and we had vanishing exploding gradient problem there also. On the left hand side in the bottom, we have that image to explain. Okay. After the encoder block, output of encoder, final encoder is sent into each decoder block so that then it can understand and predict the output. Like I like pizza will have some embedded vector of each word. These embedded vectors will be set into each decoder block and based and it depends if the decoder is in inference stage or training phase, and if it is in inference stage then it will just have this input of I like pizza as input, and it will predict something, then that prediction will go into the decoder block and it will predict another word, and then those prediction will go into a decoder block and then another prediction. If it is in training phase then it will have it will predict something, but it won't be using that prediction into the prediction of new word, and only the correct words will be sending into this decoder block during the training. We will see that, and also here we will see the mask attention, which is the like at multi-headed attention, but it will be masked in the sense that future words won't be used. We'll see that. Mask attention. Mask attention is just like encoding layer. It's just focused on a current layers and not the future words. So uh, here it is just QVK representation of in this vector format. And so, like I said, it is different with in the case of training, inference, and training, right? So this diagram is representing the training part, okay? Because how else it will know the future words anyhow. But in case of training, and we know we all send in transformer, even in decoder part, we send all the words in parallel. So how to avoid that is basically suppose it will be like a biased training of a machine learning model or deep learning model, right? Because we are sending it will be like overfitting our machine learning model because we are sending all the right answers already, but it is not predicting anything. So that means parameter will be loosely trained and it can be used on the real world scenario. So in this case, see in the left bottom left, you can see a matrix of all the V, all the K, of the all the words. It is a matrix representation of all the words. It will be added into uh, this matrix so that only those words, only current words and the previous word will remain. Or on the adding of the infinity will have very less infinite value. After the softmax layer, it will be zero, and then after this multiplication of this value matrix, we will get the this new matrix that is shown in the bottom. Let's focus here. If you don't want this, basically it is that we are just starting it. Okay, start is heavily dependent on start, and it does not know any future words. Okay, so again, me is heavily dependent on me and on the start. That it has started, and the current word is me. It does not know anything about the future. So me in this sentence is just trained on me. It is relevant on me. And in Gusta is dependent on Gusta and very less on me and very less on start. So basically, model up till now has been trained that Gusta cannot be the first word. After starting, mostly Gusta won't be the first word, and Gusta will is somewhat related to me. So me can come first, later, or in the sentence there will be me if there is Gusta. That much it has understand up till now. But even if those future words were present, because in during training we know all the words, still we are adding this negative infinity and then the softmax section so that all the future words will be animated. That is the masking of the future words, and only the current word and the previous words will be used to change the embedding of this word embedding. Okay, and then this is the value matrix like this Gusta, and then it will be the output matrix like here is Gusta, new embed. That is the masking of attention. And then again, it will have a similar multi-head attention of this mask multi-head attention. Similar to that, if you have multiple sections of this, it will be multi-head. And attention, as we know, that was previous formula was of attention only. Calculated attention score with the softmax, and then using the V matrix to get the new embedding. That is the attention. How are we embedding, utilizing our encoding, encoded output into this decoder part? That is done with the help of cross attention. With cross attention, we will get our multi this and we similar it to this encoder. We have added norm layer. It will have similar functionality of adding previous embedded vector into this current and then normalizing it into one uh, into a smaller range of vector and then utilizing that carrying forward. Okay. In cross attention, we are just uh, utilizing this encoded matrices into this decoder section so that it will have all the understanding from the encoder and then it can be used during the decoding process. So flow of decoder during training, like I explained, the result of encoder will be sent to all the decoder blocks. It will have multiple decoder blocks. Like I think in attention all we need paper. I think we have 12 decoder blocks, and current GPTs like GPT-2 I think have some 54. I think I don't know. It as it is heavily dependent on decoder only, so it will have multiple decoders. So in training phase, some output matrices will be created in the encoder block. It will be sent for into each decoder block along with current word. This starting is just one token of okay, it is started. Then it will have me and start. This above image is somewhat cut. The red line represents some output. One decoder will generate some output. Like after start, it can have lay or me or something else in Spanish. And this other decoder block won't have the input from previous decoder. It will have the correct input and the input from the encoder block. And this last decoder will also have correct input of start, me, and Gusta, and the input vector encoders from encoding block, means proper embedded vectors from encoder block. And yes, it will carry on till we have n token and it will be predicting it all the words, but it won't be utilizing uh, those predicted words. Those predictions will be just utilized to check how far off we are from this correct uh, output. Like in linear regression, also we are changing parameters correct continuously. Here also will be during training phase. All this wrong matrices will be checked, and based on that, parameters will be changed, and correct output will be generated eventually after training. Here during the inference phase, we have encoder block. It will send all the inputs, all the matrices, all the each words embedded vectors into the decoder block. It will have some starting, it will have some prediction that will go into the other decoder block, and it will have some uh, this pre first decoder has predicted me, and it will go with start and me, and then this second decoder has predicted me and Gusta. It has predicted Gusta, and it will go into the third block as start me and Gusta along with the encoder block's prediction. And the final dense layer is just we will have a very big corpus of logistic, like in simply just consider softmax matrix of multiple probabilities of 0.001, 0.002, and some of words will have 0.97, 0.87, 0. That kind of thing. So those words have higher probabilities. So after softmax, and with higher probability, those words will be have some uh, miss that word will be taken as an output. So that is the basic uh, philosophy of transform architecture. That was a basic overview of transform architecture. Transformer can be explained in the deep also of how the logistic layers are created, how the softmax are created, and that kind of things. But for now, I think that much transformer is more than enough to have basic overview of transformer. So thank you. That was my video only.